Good morning, class. Just give myself a little bit more light. There we go. Hello, 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 hello. How's everybody doing today? I hope you guys are doing well. Here we are, yet again. It's always such a pleasure. Yeah. So, some of you, we don't really have very many people here at the moment. I'm not sure why. I don't know, is there like a test going on today or something? Oh my god. Knocked over my frickin' camera, man. Jeez. Alright. Is there a test today or something? Anybody have any idea why there aren't, like, there's only like a third of the people who are usually here? Maybe it's just a slow start? Am I quiet? Hello? There we go. Okay. Alright, so yeah. I suppose, like, the week immediately before and the week immediately after reading week are usually the big test weeks, right? Let's see. Economics, discrete math, physics. Okay. Yeah, okay, that makes some sense. Well, thank you, the approximately 50 of you who came today, because, you know, we'll have some fun. This'll be your break from studying class. We'll have some fun. Maybe we'll have some Star Wars memes or something. I don't know. Anyway, no, we should probably try to catch up on the material. My chat seems slower. Okay. Well, sometimes if I pop it out, that helps. Sometimes that works. I don't know. We'll see. I love me a cup of tea. So, geology on Thursday. Ooh. Yeah, okay. So, it's midterm week. That's why nobody's here. So, before we get into the course material, can you see the cat today? Yeah. Remind me after class. I'll go grab the cat. I'll grab the cats after class. That can be our reward for having gotten through class today. Yeah, so I wanted to talk very briefly about the announcement that I put up like literally 10 minutes ago on Avenue, which is just sort of a formalization of what we were talking about yesterday in class. So, for those of you... yeah. What could be more exciting than coding a cats? Spoken like a true programmer. So, with respect to, you know, some of you may not have been here or seen the lecture from yesterday just yet. So, yesterday we were talking about the fact that the lecture material seems to have gotten behind the assignment material to the point where it's become a problem. So, what the remedy that we're going to go for with respect to that is we are pushing back. We're pushing back all of the deadlines for all of the assignments by 1 week. So every assignment is now due 1 week in the semester later than it was originally. I'm not saying they're going to 2 weeks like they're not going on a bi-weekly basis. They're still going to be weekly. We're just shifting it back by 1 week, everything back by 1 week, so that we can have some time to catch up the lecture material to where the assignments are. And the final assignment is now going to be a extra credit assignment. It's going to be a bonus assignment. And those bonus marks that are from the bonus assignment will be still category restricted to the assignments. So that might be a little bit of a controversial decision for you guys, because, you know, it would mean more marks for you if it were applied to everything and not just the assignments. However, I still want people to write the tests, and I think there's a good reason why, you don't mix those. So, that's the decision. Hopefully, it's like the prof giveth and the prof taketh away. But yeah. Yes. So, in consequence, yes, assignment 4 is due next week, not this week. Yes. So, yeah, that would be... Yeah, it's due the 7th of March. So, yeah. Yeah. I think this is a good solution to the problem that we currently have. In this rather lengthy post, I outline a few of the reasons that I feel that we've gotten into this situation. Essentially, I've never received a feedback evaluation, a course evaluation, that has not asked for more, like, code examples in class. Like, me doing code for you guys is essentially, like, where a lot of the learning happens, it seems. So I've been taking more time to do that this semester. But, of course, the time I've been taking to do that has been, I've been trying to kind of drop a few topics that are not of interest as we go through the slides. But, it's kind of... There's only so much you can gain by that. So, although we are behind in the lectures, I do not feel as if I've been wasting your time. Hopefully you guys don't feel as if I've been wasting your time. I feel like what we've been covering has been important and pertinent information to at least some of the people in the class. This being an introductory course, and, a lot of you guys probably don't have any experience programming languages. That's why you're taking the course. So it makes sense to go over the basic concepts, really hammer them in, because these are the, if you take nothing else from this course, take the first 3 or 4 lectures. Those are your essential skills. So it's kind of like a sorry, not sorry situation. And, generally speaking, people don't mind getting extensions on assignments, so, I'll probably hear about it in the evaluation that I changed this course schedule mid-semester, but, it is what it is. I did reserve the right to change that, so, you can't blame me for doing a thing I said I might do. Yes. A good question. So, the assignments are being pushed back. The test material is not the tests aren't really based on, the assignments so much as they are the lecture material coverage. So you don't have to worry about topics that you haven't seen on an assignment yet, or in lecture yet, showing up on the test, because that would just be cruel, right? No, the test that's coming up, I believe I told... Mark's coming up with the questions for it this week. It'll go up to the end of functions and recursion, and we'll be able to finish functions and recursion by the time of the test. So, yeah, don't worry. So test coverage for the test at the end of next week, consider that up to the end of topic 5, which we should be on to topic 5. Okay, I got a lot of people saying, I don't know about anybody else, but I have no background in coding, and I feel like if we were moving any quicker, I'd be left so far behind. Okay, cool. Okay, good. Yeah, I know, that being said, there are definitely people in this class who already know some programming, or even a lot of programming. I get emails from this one guy who shall remain anonymous, who always signs off his emails, yours in Java. So, if you're listening, mysterious Java friend, yes, yours in Haskell. So, for those people, I'm hoping these people can sort of quickly skim through the lectures to make sure they're not missing anything. But yeah, you guys hopefully you guys have felt like the pace has been decent so far. So is the test cumulative? It's kind of hard for it not to be at this point in the game. It's like the major new topics for the test will be data structures and functions/recursion. It's really hard to write a test that doesn't use loops, you know? So you're still going to see loops, you know, you're still going to see if statements, you're still going to need to know how to manipulate variables. You know, all of the skills that were covered in the first 3 topics or so are so essential to everything you're going to do with programming that it's impossible to say that the test is not cumulative over all of the stuff we've covered in the course so far. As we get on with the later topics in the course, things will get a bit more discrete, you know, like the testing stuff is a little bit more, you know, contained. The classes material is a little more contained. Certainly there's a unit on databases, which is entirely self-contained. So, yeah. You can think of the test as being cumulative, but it's kind of like, what's a good analogy? It's like the test is, it's like we're doing a biology class and like the first 2 weeks was DNA and then like the second 2 weeks is RNA. And it's like, well, if I test you on RNA, certainly I'm testing you on stuff that you learned from DNA, you know? It's like, anyway, perhaps I'm belaboring the point. Anyway, so let's get on to the lecture material for today. I don't see anybody complaining about the new arrangement of the assignments in the chat, so hopefully everybody is... we need to finish off this one first. Hopefully everybody's cool with the way that things are going. So, yes. Topic 4. Let's talk. We've got a little bit left to go. Let's talk about some problem solving. So, oh yeah, this is a very important example. It figures into later lectures. So, we're going to talk a little bit about algorithms. Algorithms as in you take an algorithms class and this is the type of stuff they talk about. So, problem statement. Let's imagine that you're in a store, right? And you purchase a thing, and the cashier has to give you some combination of change that equals your the amount of money that you're owed on the transaction, right? Making change, the making change process. Normally, the way that a cashier will do it is they'll give you the biggest coins as much as they can, and then move down to the smallest coins, right? So, in Canadian coinage, we have 5, 10, 25, 100, and 200 cent coins. Nickels, dimes, quarters, loonies, and toonies, respectively. So, if we had a target amount of 185 cents that we had to make change for, one possible arrangement of that change would be 1 loonie, 3 quarters, and a dime. Obviously, though, that's not the only arrangement of change that we could think of, right? You could have, 7 quarters, get rid of the loonie. You could do it entirely in nickels if you wanted to, fine. So let's write a computer algorithm that makes change, all right? I'm going to want to do this in a file. Documents... not resume, teaching, McMaster, teaching, 1MD3, winter. Yeah, see, this is why we're so far behind in classes, because I don't load up my, I don't load the thing before class, so that's where all the time is gone. You know what they say, though, time flies when you're having fun, right? So let's say get it topic 4.py. Cool. So, define, make change. What are our inputs? So, it's actually, in the same way as an assignment question, the slides are giving us what the inputs should be and what the output is expected to be. So, first, we have a tuple containing coin denominations as integers. It's very important that everything is in integers in this example, because then we can use things like exact equality and exact math. If we were dealing with floating point numbers, then we would have to worry about floating point error, so it's really just easier to use integers. That's actually one of the tricks for getting around all of the problems inherent with floating point numbers is, you don't have to use floating point numbers if you just move the decimal place back a couple of spaces. So, a tuple of coin denominations as integers. We shall call that coins. And what else are we taking? The target value. Target. What are we outputting? A dictionary where the keys are coin denominations and the values are integers corresponding to the number of coins and the denomination. So, let us first make a dictionary that contains the correct keys. Sure, we want to output a dictionary with the correct keys, so let's make one, and then we can fill in the target values, right? We can fill in how many of each coin we want once we have a dictionary that's, correctly constructed. So, let's start with a blank one. Let's construct it using a loop. For C in coins, so for every element of the coins tuple, D at C is equal to 0. And let's just print that to see what it looks like when we're finished. And of course, let's use the example that's the test case that's given on the previous page. So our coins are 5, 10, 25, 100, and 200. And our target value is 185. So, good. Let's save that up. And compile! What? There. I should be careful. Oh, syntax error. What did I do? I included a def. That was dumb. Dumb! There we go. That's better. Right. So, now we have a dictionary. We have 5, 10, 25, 100, and 200. Everything points to 0, and it returns none because it doesn't return anything at this point. And let's just throw in the penny, because rip the penny. I missed the penny. I know, but I missed the penny. I'm going to include it just for nostalgia. Let's see, we have questions. Why did I write def make change a second time? Because I was making a mistake. That's why. So that indicates to us that the dictionary has been constructed correctly, at least with respect to the keys. So now the thing that we're going to do is we're going to see if we can populate this dictionary with the correct values. So what we want to do is we want to go through each of the coins in order from largest to smallest, see how many coins fit inside the current target value, put that into the dictionary, and then update the current target value, right? That's because that's what the cashier does when she's making your change. She's like, okay, I need to give you, 1587, right? It's like 110, 15, 3/4, a dime, and 2 pennies, right? Largest to smallest. So, let's assume that the coins tuple, the coin values are in arbitrary order. So let's reorder the tuple in order to be able to work with it more effectively. So let's say coins list is equal to, we're just going to convert it to a list, because if you convert it to a list, you get a sort operation. And then if we reverse that, we should get the coins list in reverse order. And of course, in order to check that our calculation is doing the thing that we want it to, let's print what we got. None type is object is not subscriptable. All right. Let's separate that out then. Right, there you go. So there it goes. Largest to smallest. Bam. Ta-da! So what I'm trying to do here, what I'm trying to demonstrate to you is not only a method for solving this particular problem, but this is an instance of a good way of solving these problems in general, right? Take one subsection of the algorithm, do it out in code, and then print the result of just that section of the algorithm to make sure that it's doing what you think it does. Test early, test often. That's the programmer's mantra. Test early, test often. Test early, test often. So now that we have coins list in, in the correct order, we can just for loop over it because it's now in the correct order. And it, for loops take the first element and go down to the last element. So for C in coins list, we want to see how many coins of the currently considered denomination fit inside of the target sum. So, how would we do that? We would say the number of coins, and I'm just writing it directly into the dictionary here. That would be the target's amount, integer divide by the current coin value, right? So think about it. We've got, in the case where it's a 200-cent coin and 185, right? 185 integer divide by 200 is 0, right? Because it's smaller, and the whole thing would be remainder. Speaking of remainder, the target will get updated to the target modulo the coin value. Now, it's also possible, like, if you want to do more work than you have to, it's also possible to, like, do a loop where you subtract the coin value from the total repeatedly until the target value is smaller than the coin value, and at that point you stop. You can do that, but it's kind of like, sure, you can perform multiplication by repeated addition, but there's a reason we have a multiplication operator, right? So, there we go. For coin in coin list, the dictionary value of that coin is the target value integer divided by the coin value, and the target value is the target value modulo the coin value. So, let's print some stuff here as well. So print entering a loop, print target value is plus string convert target, and print what do they call this? Key or number of coins print coin value equals plus string convert C. Number of coins is equal to string convert D at C. So basically all we're doing here is we're just sort of repeating back the values that are being calculated in each of these states. So let's try it. I made an error. Prin is not defined. Prin. Where am I using prin? Did I not save it? I didn't save it. Oh. Jeez. There we go. So, entering loop. Coin value 200, number of coins 0, target value 185. Coin value 100, number of coins 1, target value 85. Coin value 25, number of coins 3, target value 10. Coin value 10, number of coins 1, target value 0. And since it doesn't, you could stop it there. Like, if you wanted to, you could add an if statement here that says if target is equal to 0, break. And then if you did that, it would, as soon as the target value hit 0, it would just stop iterating because it doesn't need to anymore, and therefore save some precious, precious CPU cycles. Although, you know, for something at this level, it really doesn't make it doesn't make much difference one way or the other whether you do those redundant cases. But, you know, in large systems, or systems where a piece of code is repeated a very large number of times, that's the sort of thing that, like, that's actual optimization. That is an example of actual optimization. Elimination of pieces of code that do not do anything. That is optimizing. Anyway, although one should never confuse the process of optimization with the production of an optimal result. Optimal, getting something to be optimal is a lot more difficult. But anyway, there's our algorithm. I'm going to see if there are any questions. I own a Canadian penny from 1909. Ha! Cool. Am I using Sublime IDE? No, I'm using GNU Edit. I'm using the Linux equivalent of Notepad. So could we go over what we're doing here again? This is an algorithm that makes change. Given a target sum and the values of some coins, it calculates what combination of coins will produce that target value of change. Cool. So let's see how our solution compares to the slides. So the procedure that we have been using is take out as many of the biggest coin as we can until we can't take out any more. Then proceed to the next biggest coin, then the next biggest coin, etc., etc., etc. Recording how many coins we take out at each step. This is an example of a so-called greedy algorithm. This is a technical term. Greedy algorithms are a type of algorithm called a matroid. Matroid, I think because it's like matrixoid, similar to a matrix. But yeah, matroid, I'm probably wrong about that. But you should talk to a mathematician about what a matroid is. Important distinction, matroid with an A, not metroid with an E. Very, very different things. Any of my Nintendo bros out there will know what I'm talking about. So, what is a greedy algorithm? A greedy algorithm is an algorithm that it doesn't look very far. It just snatches up what it thinks is, at each step it kind of snatches whatever seems optimal at this stage in the algorithm, and then proceeds on to the next stage of the algorithm. In technical terms, what we're doing is we have a sort of... It's also... This is kind of like brain exploding, so don't worry if you don't get this. But it's like, if you imagine a problem space, right? If you imagine the problem as a set of solutions to the problem, right? Like, this is actually the correct way of conceptualizing this make-change problem. There are many possible solutions to the make-change problem, right? What we are doing is we are making a decision about what part of the solution looks like, and the space of possible solutions gets smaller. We make another decision about part of the solution, and the remaining space of possible solutions gets smaller, and gets smaller, and gets smaller, until it is resolved into a single solution. That is how you solve a problem using a matroid-type algorithm. Again, it doesn't matter if you don't understand this. So, essentially, yeah, this is the slides version. They are using essentially the same method, except they're populating the dictionary with the coin values and in the same step as calculating the target values, which, you know, no reason we couldn't have done that. But they're also assuming, one of the assumptions on this particular one is that this tuple be in a particular order, whereas we are assuming the tuple is in no particular order. That's why we're performing this sorting operation, right? To get it in order so that we can deal with it in order. So, here's a question. Does the greedy algorithm always give you the smallest number of coins? So, if you consider the space of solutions to the make-change problem, it's difficult to say what solutions to the make-change problem are preferable to others unless you, like, think about it a little bit, right? You have to sort of impose a system of valuing the answers on this space of possible answers to be able to decide whether or not a solution is a good solution or a bad solution. So, to the make-change problem, you can imagine, if you were an actual cashier, a bad solution to the make-change problem is to give the customer exact change in pennies each time. For one thing, you'd run out of pennies very quickly, and for another, the customer certainly wouldn't appreciate it, because it's like, all right, your change is $15. Here's, like, 1,500 pennies, all in rolls. It's like, how am I going to put this in my wallet? This is stupid. So, obviously, the solution where we produce the maximum number of coins of all of the solutions, that's like our touchstone for the worst possible solution to this problem, right? So, by process of logic, one might say, well, if having more coins is not preferable, then having fewer coins will be preferable. So, we can define the optimal solution to the make-change problem as that solution which produces the smallest number of coins of any solution, right? We are optimizing for the least number of coins. Cool. So it turns out that the greedy algorithm doesn't necessarily give you that, although only under certain conditions. So if we modify our original algorithm, in order to, if we replace, if we insert a coin of 7 cents value into this, and then we ask for 14 cents worth of change. Here's an interesting, here's what happens. Oh, actually, you know what? I'm forgetting to actually return the dictionary. Okay. All right. Yeah, they put me in charge of teaching people, you know. Cool. So, the solution for a list of coins that includes a 7-cent coin, which I know doesn't physically exist, but imagine it, like, for the purposes of math, okay? And if we're going for a target value of 14, obviously, the fewest number of coins that you can produce from that set is 2 7-cent coins. Right? That we can look at that and say that's obviously that's what we should be finding there. However, what the actual algorithm comes up with is 1 10-cent coin and 4 1-cent coins. So 5 coins in total. And of course, the reason it does that is because it goes from largest to smallest, and if the largest fits, it takes it, regardless as to whether or not that's an optimal solution. So it turns out that you can reproduce this situation anytime you have a coin value that isn't at least twice whatever coin value was before it, right? So because 7 is not at least twice 5, that's what produces the mathematical conditions under which this can happen. So how would you modify your algorithm to be able to come up with the optimal solution in this case? And the answer is, that is a hard thing to do. Like, essentially what it requires is backtracking. You need to, when you make a decision, you need to sort of put an asterisk by that decision and say, okay, I'm assigning 10 here, but I'm not sure that it's going to be the correct solution, so I'm going to try some other solution, see if I find a better solution, and then pick the best solution. You would have to write an algorithm to do that, and of course that makes the algorithm way more complicated. Immensely more complicated. So this is actually an example of what's called an MNP Hard Problem. NP stands for non-polynomial. So this is we're going to touch a little bit on this kind of stuff in this course, but essentially you can classify the runtime of algorithms based on their structure, and it turns out that you can certain types of problems correspond to certain structures of programs, and you can deduce from the structure of the program, or you can measure it empirically, pardon me. You can determine how quickly the runtime of the algorithm increases when you increase the size of the things you put into it. This is roughly the mechanism by which algorithms are classified in terms of their efficiency, right? So if you have an algorithm that only takes 1 CPU cycle more for every additional, element in the array that it processes, that's like a constant, that's a linear time algorithm, because the amount of time that it takes to execute increases linearly with the size of the input. In this case, it's a non-polynomial algorithm, which means that it might be exponential. So 2 to the power of n, where n is the number of things. If you graph that function increases so rapidly with in comparison to something like a linear function that you can very easily hit the limits of your computational ability with your computer trying to process these types of algorithms. And it's interesting because I was actually contending with these types of problems during my thesis research. I had to come up with clever ways of getting around the fact that I was essentially working on an NP hard problem. But yeah, so just one more note about that. In computer science, we have this notion of NP completeness, and an idea of the solution to P is equal to NP. You sometimes might see t-shirts that say P equals NP. I keep the faith. P can equal NP. So essentially, and this is kind of getting into computer science research, but the problem with NP hard problems is that there is no proof that they can be run in polynomial time. Now, of course, in logic, absence of proof is not proof of absence, right? So just because you don't have a proof just because there's no proof that something is a certain way doesn't mean there couldn't be, right? It's different to prove, like, you can prove things can be something, and you can prove things can't be something, right? But a lack of a proof doesn't necessarily indicate that the thing you're trying to prove can't possibly happen. Although most serious computer scientists have sort of come to the consensus that although there's no proof that these super hard problems can be solved easily, it's probably the case. We probably would have found it by now, so unless some mathematical super genius wants to come and prove to us that P is equal to NP, that is, these super hard problems can be solved using some weird algorithmic arrangement, we can solve them in polynomial time, we're gonna trust that probably can't be the case. Incidentally, if anybody ever finds out the solution to P is equal to NP, that basically breaks all encryption everywhere. Because the reason encryption works is because decrypting is an NP hard problem. Yes. Anyway, let me see if there are any questions. Am I talking about big O notation? Yes, I am talking about big O notation. I was trying not to use the term big O notation for some reason, but yeah, if you know what big O is, I'm talking about big O notation. So yeah, yes. Quantum computers can theoretically solve NP hard problems in linear time, apparently. Although I haven't like read the papers or anything. But yeah. Anyway, that's topic 4. Congratulations. Let's move on to topic 5. Ho-ho! Are there any questions about topic 4, though, before we move on to topic 5? I realize we don't have much time left in the class, but we're not in a position to be wasting any of it. Is my camera stuck? No, it's good. Okay. Okay, I'm gonna move on then. Speak now or forever hold your pieces. Okay, so. Let's talk about functions. You've been using functions. Functions are a thing you've had to get used to the idea of. You have been using functions in the assignments. Functions are very useful. We're going to talk about functions. We're going to talk about all of the interesting and crazy things you can do with functions. There's a lot. So let's get started. So, I shouldn't have to review this, but we're going to talk about it very briefly. A function is a way of grouping together a sequence of operations under a common name so that it can be referred to multiple times later. The idea is very similar to the idea of a mathematical function, like cosine, exponent, logarithm, etc., etc. When you use cos, you know what cos is because cos is defined. The same thing with functions, except you're the one who's defining them. This is the syntax. I'm not going to go through this because if you don't know the syntax for if you don't know the spin tax for functions, then you should by now. Go review like a few. Oh my god, the slides, stop misbehaving. There we go. You should know the syntax for functions by now. So here's an important piece of nomenclature though for you. So you provide these arguments at the top. In Python, we call these formal parameters, and we call the variables that are provided when you actually call the function, when you invoke the function, we call those the actual parameters. So, formal parameters, actual parameters. The formal parameters are used within the context of the function. The actual parameters are not. They are only inside of the function if they've been defined as global. So, during function invocation, there is an implicit step where the actual parameters are assigned to the formal parameters. That's because Python uses pass by assignment. Because it uses pass by assignment, all of the particular caveats of the assignment operation are applicable in that operation as well. So, one of the effects of this is when you pass a list into a function, the assignment operation means that the list, what you're working with, is an alias of whatever list you put into it. Alias in the same manner that we were dealing with aliases in the previous topic. So just keep that in mind. Okay? Yes. So pass by assignment. That's totally a thing. Let me see. We have any questions? Cool. So here's a kind of a cool thing. Did you ever want to include a parameter that you didn't necessarily want to actually have to provide? You wanted to give the user the option as to whether or not they provide something for it? Well, you're in luck, because we have a thing called default parameters. So if you include this assignment statement, it's not technically speaking an assignment statement, but it looks like an assignment statement. If you include this thing inside of the declaration of a function, what this means is if this value is not provided, I'm going to assume it's true. And you can assign it to whatever you want, right? So, yeah. So in this example, no, let's, I want to do an example. Let's do it down here. So let's say, let's do exactly what they want. Sort values ascending. So I may not have spelled that correctly, but whatever. We will set ascending to a default value of true. So if ascending, then value return values dot sort. Else v is equal to values dot sort return v reversed. You could also do sort dot reverse. I think that also works actually. Let's do it that way. So if we sort just random values, sure. If we call this, I need to print it. Print. If we call this, I need to, what? None. That doesn't make any sense. Sorty. Maybe it doesn't like me using the name sort. None. Oh, I get it. Yeah, the return value of the sort function is Yeah, okay. Well, anyway. V is equal to values.sort return V. Try that. Okay. So, despite the fact that I have not yet, I do not yet have the ability to actually return the value, when called without the second parameter, it assumes true, so it executes this branch. However, if we specify, and I know it's time, but if we specify a value for that function, it executes the other branch, and it's, yeah, okay. There. See, it executes the opposite branch. So it's a way of being able to include a value or a parameter that's optional. You have the option of whether or not to do it. Lots and lots of library functions have options on them, and this is typically how in the Python source material, the Python prelude, that's how they do that. Like, for example, Python 3 help print. Notice print has all kinds of optional values. So yeah, anyway, I think that's class. If you have any questions, please leave them in the comments. Return values at the end. Yeah, probably. If you have any questions, please put those in the chat now. I will stay on for a little bit, and otherwise, I'm gonna go get me some lunch. Lunch, lunch, lunch. The most wonderful part of the day. Lunch, lunch, lunch. I've got to eat my lunch today. The professor rhymed day with today. Well, it wasn't a poetry class. Yes! The cat! Yes! Okay. 1 second. Boop. Hello, everyone. Whoop. This is Remy. Remy says hi. Say hello to the people, Remy. She was sleeping. What's for lunch? Probably ramen. Oh, no, there's still some chicken fingers left over from last night's dinner. Last night I made chipotle mayonnaise, and it came out pretty well. You guys ever have you ever made mayonnaise? It's actually really cool and doesn't take very much time, and it's so much better than any store-bought mayonnaise, like, honestly. Oh, I think I have a question. Yes. Yeah, you have to nourish your body so that your brain has lots of coding thoughts. Yeah, yeah, so, in order to make mayonnaise, you take, 2 egg yolks. Spoop. Spoop, spoop. 2 egg yolks. About a cup of canola oil, or some sort of light oil. Olive oil doesn't really work, it's too heavy. And you can put, like, a little garlic powder in it, a little bit of salt, maybe, in my case, I was making chipotle mayonnaise, so I took some chipotle sauce and I put it in, and a little bit of honey. And then you take your immersion blender, if you have an immersion blender, and sorry. she didn't like that. You immersion blend and a little bit of vinegar. Not too much vinegar, just a little bit of vinegar. If you immersion blend the egg yolks and the vinegar and all of the spices together, and then slowly add the oil as you're blending, you get the best mayonnaise that you would ever have, and you get to choose how thick it is. You can use whole eggs too to make mayonnaise. Oh, interesting. Where's the other cat though? Ooh, I can go grab him. You can use whole eggs. That's interesting. Big cat. Hello. Oh, kisses. Yes. So, yeah, basically the situation was like, we decided that it was a chicken fingers night, and Allie was like, you know what? We should probably have a sauce to go with chicken fingers. Plain chicken fingers is just sad. And I was like, okay, I will go to the 7-Eleven and see if they have any plum sauce. And I went to the 7-Eleven, which is like right across from the house, and there was no plum sauce. And I was like, well, I suppose I could buy like chip dip. But they want like $5 for a jar of it. I bet I could do better. So I decided, I came home and I said, okay, we've got 3 options. I could make like a cheese fondue dip. I could make a mayonnaise-based dip. Or I could try to make something approximating plum sauce by diluting jam and then adding cornstarch. And she's like, do the mayonnaise. So we did the mayonnaise. Kiss, kiss. You have to, no, you can't just run away. You have to be a people kitten. Yeah. It was actually his 2nd birthday yesterday. Woo! Say hello to the people in the internet land. Cool. You should try making your own sauces. It's like it's so satisfying to have a mason jar full of mayonnaise and be like, I made this. It's delicious. Would I ever get a dog, and if so, what kind? You know, that's actually a Allie and I have been talking about getting a dog at some point. Like, maybe when the kids are, like, a little bit, meh, I don't know. I feel like a little boy should have a dog, you know? But, yeah, I don't know. Beagle? Beagles are a good breed of, they're a fun kind of breed to have around. I wouldn't do something like a husky. They're just, like, the bigger the dog, the more work they are, you know? Yeah, I don't know. I certainly, huskies seem to be pretty popular in my neighborhood, but I'm not a big fan. Like, I don't want to walk a dog and then also have to ride the bike at the same time. Samoyeds. Samoyeds. Is that breed? I don't have my phone with me. Let me see here what you're talking about there. Poodles. Yeah. Yeah, I could see a poodle. Poodles are hunting dogs. I don't know, if it weren't a beagle, I'd probably be, I know I just said big dogs are not my style, but I'd probably do like a retriever, like a lab retriever or something like that. I don't know. Likely what we'd do is we'd just go to the pound, see what needs adopting, and, you know, take it from there. At one point we did the that like quiz thing where like it's like match you up with a dog breed, and it said that we should do Eskies. Apparently that's like the most intelligent oh that's nice. Most intelligent dog breed is the Esky. Oh, they're so fluffy and cute. Look how fluffy and cute they are. It's absolutely amazing. Yes. Retrievers aren't big, Mastiffs are. That's true. Yeah, the only disadvantage of having a Mastiff is that when you bend over to pick up the poops, they are human size. Uh, or possibly bigger. If you want a dog you can ride, get a like a bull Mastiff. But yeah. Yeah, you know. Anywho. Japanese Spitz. This is what class is now. It's us looking up dog breeds. Oh my gosh. Ah. You know, they don't actually look... They don't look super different, actually. Yeah. My wife Allie, and on her side of the family, Cocker Spaniels are traditional as well. And I think I'd be fine with a Spaniel. You know. I'm not actually that picky. You know. But, yeah, anyway. Anywho, I gotta get lunch, and you guys gotta get studying because of all these midterms. So, thank you very much for attending Mr. Moore's Cute Animal Hour, and take her easy, folks. Remember, if you're feeling too much stress, deep breathing. Deep breathing exercises are extremely good for stress. They lower your heart rate, they lower your cortisol levels, you can focus much better if there's some oxygen in your brain. Take her easy, folks.